Hello everyone, we'd like to start today's lecture by talking about control instructions. So what are control instructions? They are instructions that perform some kind of testing or some kind of a loop effect. So usually some of the control instructions we see in programming is if else, for loops, while loops. So all of these can be done using a MIPS instruction set. For this we have two types of control instructions. They are called conditional branches and unconditional jumps. So with the conditional branches, these are based on a certain condition. We execute the branch. Some of these instructions are branch if equal, branch if not equal, this branch if equal, branch if not equal, and here we have jump instruction J, just like this, jump. We have jump register and jump and link, Of course here we have many other branching instructions, but we're going to focus just on these two. So typically the program memory or any code executes in a sequential matter. So here we start, let's say we start the program here, and then we execute. So this is instruction number 1, instruction number 2, instruction number 3. Each instruction is executed at a time. However, with branches, what we have is that in the program memory we have an instruction that jumps several locations based on some condition, or jumps for no condition. So we're gonna start our discussion by the conditional branches, and we're gonna go ahead and discuss how it works. So let's talk about conditional branches. So the first instruction is called branch if equal. It's called BEQ. It has takes $rs, $rt, and a location that it will go to. So what this does is, if register file of rs, the content that's inside the register file, is equal register file of rt, we would like to go to label. So assume we have some sort of a dummy program. Say this is label, and here we have some instructions, and then at the end we say branch if equal or branch if not equal based on our code. Let's say $s0, $s1, and then we go to label. So here we're saying that if these are equal, then we go there. So condition true. Otherwise we continue executing the program. So here we can see that we have some sort of a if-else condition, for example, or no, actually it's just like a loop probably. Since we're going multiple places up, we can create loops, we can create if-else conditions using this, and we're going to discuss this shortly. So let's say I would like to create a loop for 10 times. So first I need to store a variable 10. So there are two ways of doing it. I'm going to show you the easy way, which is just subtracting until we reach 0. So what we want to do is for example, I equal 0, I is less than 10, I plus plus, just do nothing. Nothing translate to in MIPS to no operation, nope. So to do this in MIPS, first we initialize a variable. What we're gonna do is we're gonna use S0 and we're gonna initialize it to 10 like this, and then we're gonna add this label, it's called the loop. And first we're gonna say nope, this is the body of the loop. Now what we want to do is we want to subtract each iteration. I'm gonna go and do no operation or whatever operation I want to do. I want to subtract from this 10 to be 9, 8, 7, 6 until I reach 0. So what I do is I do add I door S0 door S0 minus 1. So here I'm subtracting minus 1 from 10, so it's gonna be 10, 9, 8, 7, and then I'm gonna reach 0. So I'm not gonna use branch if equal, I'm gonna use branch if not equal dollar S0 dollar 0 loop. So what happens here is that when I reach this instruction, the first iteration is gonna be 9. So 9 is not equal to 0, so it's gonna branch the condition true. So this will happen the first time. Then it's gonna subtract it again, it's gonna be 8. So I'm gonna start with 10, 9, 8, 7 until I reach 0. When I reach 0, I'm not gonna loop again, I'm gonna exit the loop. Alright, and if I look at this code in the program memory, it's gonna be like this. I'm gonna have here the add I instruction. I'm not gonna write the whole thing. Then we have loop. It's not part of the code, just pointing to a place where I want to go to. So I have this is no operation, then add I, then I have the branch not equal. So actually I'm going here each time the condition happens that it is not equal to 0. So this is a for loop being translated to MIPS assembly code. Now let's say I want to do something else. I want to do some if-else conditions. So let's start now with if-else conditions. So let's say I want to create an if-else statement, and now with this if-else statement I'm gonna do a program like this. If I is equal 10, I'm gonna say G is equal H plus K, else G is gonna be whatever J plus K. So first I need to store this 10 somewhere in a dummy variable. So I'm gonna initialize it to T0 or 10, and then I need to test it. So I'm gonna say, let's say I is S0, this is S1, this is S2, S3, and this is S4. So of course I need to assign each variable to a register. So now what I want to do is I want to compare S0i to 10. So I say branch if equal dollar S0 dollar T0 comma, I'm gonna use equal. This is the label. So if this condition is true, I'm gonna go to equal, else I'm gonna use here an unconditional statement which is called jump. It's just, it goes there, whatever the condition is, does not have any condition. So I'm gonna jump not equal. So if this is equal, I'm gonna say what do I need to do? I need to add h to k and store it in g. So I'm gonna say add dollar s1 dollar s2 dollar s3. So I'm gonna add h to k and store them in g. And now I need to add, I'm gonna keep a distance here, and what's not equal? I'm gonna add dollar s1 to dollar s4 dollar s3. So I'm saying g is equal j plus k. Now I need to add another, so these will not happen next to following each other. I need to add an unconditional jump here to exit somewhere out. So if I follow the path of the program, it's gonna put in t0. If it's equal, it's gonna go like this. It's gonna add those instructions and then exit. Otherwise, if I want to check the other one, it's gonna be, if it's not equal, so I test it, I'm gonna go to not equal, which is here, and then continue here. So I'm gonna jump over these two. So this is a way to do an if-else condition. So here we got introduced to two different types of jumps, a conditional jump and an unconditional jump. So branch if equal will actually go to equal if they are S0 and T0 are equal, else it will just continue executing. So this is the condition is true, the condition is untrue. However, when I reach jump not equal, this label is not equal, so it will go there regardless of the outcome, or there's no outcome here because there's no condition to be tested. So this is an if else. So we saw how to do a for, we saw how to do an else, we got introduced to the jump instruction, which is a J format instruction. Now let's talk about the binary representation of this instruction, which is a little bit challenging. So in terms of branch of equal, $rs, $rt, and the label. So what happens here is that it's an I format instruction. Okay, so if you look at the I format instruction, it has an opcode, RS, RT, 6 bits, 5 bits, 5 bits, and then we have 16 bits for the immediate. So here we have a problem. As we know, the program memory has 32 bits for the instruction and an address of 32 bits. So how come the branch knows how to reach the address that I want to do? So let's say start is here, this address 0x, let's say 0a b 0 1 0 0 0. Okay, so this is the address of start. We have the instructions, and then let's say the branch of equal is here, and $s0, $s1, and start. So here, this address assume is gonna be 0x, 0a, b, 0, 1, 0, let's say 4, 0. So here we have many instructions between them, and I want to calculate, or I want to translate branch of equal to binary. So we know from the MIPS reference sheet that branch of equal has an opcode of 4 hex. So this is represented in 6 bits, so we need to write something like this: 1, 2, and then we have 0, 1, 0, 0. So these are the 4 bits for the opcode. Now, for branch, they use something called a relative address, which means I don't give the complete address here, but actually I give the displacement between them, or actually the difference between them. And the way I do it is with a simple formula. I say PC target, in my case it's gonna be start, is equal PC old or PC branch plus 4 plus 4n. So first of all, what's PC? PC is the program counter. It's this guy here which tells me what instruction should I execute. So PC indicates next instruction to execute. So let's say I'm here. The next instruction to be executed is actually PC plus 4, because PC, whenever I want to execute an instruction, during execution PC is incremented by 4 automatically before finishing executing this instruction. So this is why we have this plus 4, and then we have this 4n. So this 4n is actually the number of instructions between these two. So n is the number of instructions between branch of equal and target. Why it's multiplied by 4n? It's multiplied by 4n because it is byte addressable. So whenever I want to find the displacement between those two, actually this number, this address is the byte address of start. So this is byte number 0x0AB01000. So now to do this calculation, let's go ahead and apply the formula. So we said PC target is equal PC for the branch plus 4 plus 4n. This n will be the immediate that I am searching for when I want to translate to binary. So now the PC target will be 0x0. Let's look at again. This is the target. This is where I want to go. So this is going to be 0x0 AB01000. It's equal. What's the PC of the branch? It's going to be with a 40. 0x 0AB01040 plus 4 plus 4n. And now if I go ahead and do the additions, it's going to be 0x 0AB01000. I'm going to add and subtract and take it to the other side. 0x 0AB01044. Okay, this is going to be equal to 4n. You can use the same terminology. So now if I subtract these two, I'm going to have minus 0x, of course, 0.0000044, and this is going to be equal to 4n. Now I need to divide by 4. The easiest way to divide by 4 is actually I'm gonna translate it to binary and shift it left by 4, or actually if I want to divide by 4, I'm gonna have it divided by shifting them right. So we can easily say, or we can just do the division. N is gonna equal 0x 0.0000011. So minus. So how can we write this? Of course, we're just gonna take the 16 bits, so just this part, okay, because the immediate is 16 bits, so this is going to be 0 0 0 0, and then we're gonna apply 2's complement to this. So what we're gonna have is 1 1 1 1 first complement, 1 1 1 1 1 0 1 1 1 0, then add 1, so the address will be 1 1 1 1 1 1 1 0 and 1 1 1. This will be 0x f f e f. So this is the immediate. Now if I want to write it in binary, I know the opcode is 4, so this is 0 0 1 0 0. Okay, we're missing a 0, so it's going to be 0 1 0 0, and then okay, let me write this again, it's not clear. 0 0 0 1 0 0. This is 4, and then we have we use which registers we used. We used where's the branch? S0 and S1. So if I check S0 and S1, they are 16 and 17. So this is going to be 16. So let me write it tightly. It's 5 bits. So it's going to be 1 0 0 0 0, and then 1 0 0 0 1. And here we're gonna write the immediate, which is going to be 1 1 1 1 1 1 1 1 1 1 1 0 1 1 1 1. So this is the instruction in binary. Now concerning the conditional unconditional jumps, with the jump format, jump address, we have the opcode. It's going to be 6 bits, and the immediate here is going to be 26 bits. So jump address use something called pseudo address, and the pseudo address, the way we compute it is it's just a fake address, or not the complete address. So let's say we're going to use the same addresses again, 0 a b 0 1 0 0 0, and this is start, and let's say we have some instructions, and then here we have jump jump g start. I'm gonna take this out, start, and this is 0x0 a b 0 1 0 4 0. In the case of jump, we don't care about this address, we just care about the other address. So the first step is we're gonna transform it to binary. So it's gonna be 1 2 3 4. This is the first one. A is like this, B is like this, then we have another 0, then 1, then we have zeros. Okay, so this is in binary. So this address is 32 bits. So we need to transform this 32 bits into 26 bits. So the first thing that we do is actually take the four most significant bits, these bits. So these, we're gonna take them out. The reasoning behind this is that we don't take that much for jumps. So jumping for, let's say, 28 bits is long enough jumps. And then since, so these bits are taken off. So what we have is 1 0 1 0 1 0 1 1 and another zeros. Now we're gonna 1, and then we're gonna have 0 0 0 0 0 0 0 and another. So these are, now we reach the place where we have 28 bits. Now, another reasoning, another 2 bits that we can remove is the last 2 bits. So why do we remove the last 2 bits? Because we know for a fact that the program memory is byte addressable. So if I take a look at the program memory, it's going to 0, 4, 8, 12, and so forth. And we notice that the last 2 bits are always 0, so we can take them off. So the jump address that is going into this 26 bits is 1010, 1011, 234, 1, and then 1234, 1234, and then 2 zeros. So now I can write it in hex if I want by taking 4 bits at a time. This is 0, this is 0, and this will be 4, another 0, this will be C, this will be A, and 2. So this is the address in binary. So this value will go directly into this 26 bits. So this is the translation of the jump instruction to binary. So this will conclude our lesson for jumps and branches. Next lecture we're going to start with the hardware design.